Now, I don't have to do the same mistake again. So I'm going to introduce to Professor Andrew Blumberg. As you can see, he's also a very young professor. In fact, he's professor at the University of Texas at Austin. But he has been in the last year also at IMA, like Mike. And he has also been around the world, you know, in the main center for topological data analysis, at least inclined to algebraic topology, is in Stanford. So he has been in touch with Gunnar Carlsson and his group in Stanford for the. In fact, he just flew from San Francisco. He got his PhD at the University of Chicago, working under the supervision of Peter May. Peter May is one of these classic algebraic topologists. Even when I was a grad student in England, he was already a well-known algebraic topologist, this famous Peter May. So Andrew got a PhD from Peter May in Chicago back in 2005. So, you know, he's still quite young. He defines himself really like an algebraic topologist. You know, when you see his very short CV, he says that primarily he works in homotopy theory, in algebraic topology, with focus in algebraic K theory, and so on and so on. I mean, you know, he defines himself as an algebraic topologist. But when you talk with him, and I've been talking with him since last November, you will see that he is really interested in very many applications related with data analysis. So it's really my pleasure to introduce Andrew Blumberg in this panel.
Okay. Well, thank you for the introduction, and thank you for the opportunity to speak. I need to, however, take 90 seconds to change the slides on the computer. Okay. There we go. Okay.
What you do down here?
No, I'll do the same thing that Mike did. Okay. So I want to pick up where Mike left off and tell you something about integrating statistical methodology and into the practice of topological data analysis. And the goal is to give an overview. There's been a lot of work on this in the last, I think, 5 years. So this is an interesting field. Let me pause to give some background. Insofar as this was started by algebraic topologists who largely didn't know any statistics and didn't know very much computer science. And as it's matured, there's been a tremendous infusion of ideas from both of those disciplines. I want to talk about the last 5 or 6 years, or a survey of ideas coming in from statistics. Some of this will be somewhat mathematical, but all of it should have a slogan or a lesson that you can take home about how to think about how to use topological data analysis and some of the challenges that come up in that. So the integration with statistics is absolutely essential for using topological data analysis to do anything, because it provides ways to understand what the results mean. And I'll give you some pictures to say more about what I mean by that. It also provides a methodology for handling noise, which is a big problem. With any actual data you get, you're going to have corrupted points. You're going to have noise in the sensors. I mean, who knows? You might or might not have a model of where that noise came from. And the other thing is that one issue with this is, so topological data analysis provides richer features than you would get from doing a traditional linear analysis, from doing a regression or a PCA. You get much richer descriptors from this. But the cost is that it's true that, as Mike said, that there are wonderful algorithms that are remarkably efficient for doing this, but they're still slow enough that on very large data sets, it's a real problem. And some of the statistical ideas, in particular ideas about resampling, help us grapple with that. And so this is all, as I was saying, particularly salient when we're thinking about big data applications of these tools. OK, So let me just, Mike just told you, and let me encapsulate. So the way this works is you start with your data, which is what I'm going to think of as a finite metric space. So it's a bunch of points and distances between them. The pictures that Mike was showing you, those points are sitting in Euclidean space. So they're just some vector of numbers. And from that, via this process of blowing up balls, you produce a series of topological spaces. And out of those spaces, you produce this picture called a barcode. Now, an important question is, what does this barcode you see mean? And how can you be precise about that? And let me now show you some pictures. So this is a version of the picture that Mike showed you. And here, maybe this is very easy to understand, insofar as you can see it, anyway. There are these two circles. And as you blow up, at the beginning, there's some sort of little noise from when points come together. And then after a while, there are two long bars in the barcode which are capturing the fact that there are two circles in this figure 8. Okay, and this is very easy, and we think when we look at it, you know what it means. But, oops, there we go. But suppose your picture looks like this. So this picture, we have one large dense circle and one very small circle at a different density. And as a consequence, what you see is the bars, you have two long bars again, but one of them is much shorter than the other and only lives for a little while. And one thing to notice about this picture that should be alarming, if you think about it, is that on the left, I didn't count those, but I think there may be 200 points there or something like that. On the right, there are 5. And this is bad, right? Because this is telling you that by 5 well-placed points have almost as much weight in that picture as 200 dense points. And those 5 points might well be noise, right? This is indicative of the kind of problems with robustness that these methods have. Another one is that, and this is maybe a much more important issue, we're showing you, both Mike and I are showing you pictures that come from donuts and coffee cups so you can understand. But if you actually took your data and did this, you wouldn't see a picture like that. You would see a picture like this, if you were lucky. Your picture would probably have 300 bars in it. And what does that mean? It's not, in some sense it means there are holes, but how can you pull those out? So, and let me reflect a little bit more on what these things tell us. One thing is that your data set this is about geometry, but your data set might not have come from something where you can understand what the geometry is. If I take data about incomes in the Bronx in New York, and I plot them, and then I do topological data analysis, I'll get a barcode. But it's not really clear what the geometry of incomes exactly should mean. I mean, you want to tease one out, but a priori you don't know. And it probably didn't come from a manifold. Data, as both Mike and I have shown you pictures about, data has features at different scales. And you have to think about how to integrate those scales across your representation. Another thing is that the output of this might be more useful as a signature rather than something where you can actually point to a hole in the object. And finally, even very small amounts of malicious corruption can arbitrarily change the output if you're not careful. So I want to refine this pipeline to incorporate statistics. And the way you do this is to think about where did these points come from. And the formalism is that the points came from sampling from a metric measure space, which you can think of just as I have a space, I have distances between the points, and I have some computable procedure for sampling from it, for producing new samples. And maybe this is because I can actually take new data, and maybe because I have a very large data set and I'm taking little subsamples from it. There are different ways to think about this. And the refined pipeline is now going to be that I start with a metric measure space, I take some samples and get a finite metric space, I get a filtered topological space, and then I produce a barcode. And this leads you to immediately want to think about distributions of samples on barcodes. That's the object that you really are studying. So to make sense of this, we have to maybe not fight with the technology. To make sense of this, we have to think about the structure of the space of barcodes. And one of the things that makes this subject go is the fact that barcode space has a lot of structure. These pictures themselves have a distance. And this is the formula, but maybe I just tell you, the way the distance works is I want to think about the distance between two barcodes. I match up the longest bars, and I look at the discrepancies between them, and then I take the worst of the shortest bars that wasn't matched, and I add that in too, and I take the worst score amongst all of that, and I take that over all possible matchings. So I overlay them, and I look at the difference, right? And there are other metrics, but basically what this means is that if it's less than epsilon, then there's a discrepancy of epsilon both in the matched and in the unmatched bars. And what you want to know is what kind of metric space is this? And the good news is that this is a space where you can do probability theory. And this is work of Maleko and Mukherjee and Harrer, and other people have versions of this. But you can, this is a nice metric space. It's a Polish space for people who know about those things. The bad news is that this space is positively curved. And let me tell you what that actually means. There aren't, in the barcode space, there aren't unique shortest paths between points. So everyone's favorite example of a positively curved space is the Earth. And if you think about the unique, whether there's a unique shortest path between antipodal points on the other, opposite ends of the globe, there aren't. There are lots of ways to get between them. Now, why we care about this is because the first question you might ask from a statistical perspective is, what's a summary? What's the average of a collection of barcodes? Or what's the mean? Or something like that. And there's a problem, which is that because this metric space is positively curved, you can't define centroids or averages in a very good way. People have done nice work with Turner and Maleko and Mukherjee and Harrer on what are called Frechet means. But they're in principle, not in principle, in practice, they're very difficult to compute. And they have surprising properties. Another thing you might do, and this is in practice what people do, is figure out a way to, we went to all this trouble to turn our data into some sort of barcode picture, is to project it back into R, where we know how to do statistics. And how do we do that? So if we have some sort of reasonable map to R, I have a distribution on barcodes, which is a sensible object, and I produce a distribution in R, and I can do statistics there. And there are lots of sorts of maps into R. I could take the length of the longest bar, or the ratio of the endpoints of a bar, or the difference between two of the bars. And you can probably invent a dozen others during the boring parts of this talk. There's another approach, a more structured approach to this by Bubnik, involving embedding it in a function space, which maybe I won't say so much about. But now we have a way to get robust statistics of barcodes, because I have my data, I sample from it a bunch. I get this distribution on barcodes, I push that into R, and then I take a robust statistic there, like the median, and that's a statistic of the distribution of barcodes. And that's the general picture for how statistical practice is going to work here. So what this suggests is that the basic invariant you're studying here is really the distribution of barcodes you get by looking at all samples of size n for some fixed sampling rate from your data. And although in principle, of course, you can't have all the samples, this is easy to approximate in practice just by taking lots of them and forming the empirical distribution. It's efficient in the sense that one of the problems with this is that if your data set has, so the data set, the example that Mike presented of the natural image statistics is a very good example. There were originally something like 1 million points in that data set. Someone spent a great deal of time taking pictures of Dutch cities and the Dutch countryside. And they winnowed that down by very complicated filtering procedures to get down to the 5,000 points that they used. And even then, they did some further things to reduce the number of points to make it computationally tractable. Here, the notion would be that rather than thinking about the best 5,000 points, you might just, with your very large data set, you might just think about some approximation to the ensemble of all subsets that are of size 300, or size 500, or of whatever size you can afford to run your algorithms on. So this is tunable and scalable depending on how much computer power you have, and it's naively parallelizable. It's also robust to noise. When you're sampling like this, low-density features don't turn up in very many of these samples. And so it's very easy to discount them. And you can say precise things about that. And this is, in some formal sense, this is stable to changes in the distribution on the underlying metric measure space. OK. So the efficiency point is one that's worth making. And this is one of the sort of skeletons in the closet about the area. And maybe it's early in your relationship with it to learn these things. But one of the issues here is that if I have a very large data set, and I think about the procedure that Mike was describing of blowing up these balls, at the end, right, when my radius is very large, all the points are going to be connected. Now, from a topological standpoint, that's boring. That's the contractible object, and it has no Betty numbers of any kind. From a computational standpoint, that's a disaster, because it's that if you think about what you're doing, you have an edge for every pair of points, and you have a triangle for every three tuple of points. And in fact, you have 2 to the n simplices to worry about in your discrete representation of this geometric object. And that's bad. I mean, what that means is there's an exponential dependence, essentially, if you don't choose your feature scale carefully for computing these. And people have done a lot of work on approximation methods, which is very good. But many of them depend on the feature scale, and many of them it's unclear how they apply in practice. And the perspective that I want to sell you on in brief is that this perspective of distributional invariance. The idea is that to handle very large data, for big data applications, you should look at distributions of analyses of small data that you can understand and assemble that, because it's easy to compute. So yeah, so again, this is necessary for potential applications. Now, once you do this, so let me say a little bit more about statistics beyond means and medians. One thing you immediately might want to do is do hypothesis testing or find confidence intervals for quantities of interest about your data. Right? You want to make guesses about it and see if the data bears that out. Doing this directly in barcode space, and this is again an issue with working here. Doing this directly in barcode space is that it's hard to specify what you mean by a topological null hypothesis. I mean, this is a problem. This isn't just about topological data analysis. This is a problem about big data, is that it's often, with large unstructured data sets, it's often hard to have well-informed, good models of what the alternatives might be, or what the universe of possible structures you might be seeing to sort of select amongst might be. But it's particularly bad for thinking about the space of topological analyses. And even, a first question you might ask as a mathematician is, supposing I take random noise in a box and I do this, what are the formulas for what I see, for the lengths of the bars that come out of this? Can I describe those asymptotically? And the answer still is no. So there's lots of, for the people who are mathematicians, there's lots of interesting work to be done, despite the fact that there's been a lot of very good work at fixed scale by Adler and Bobrowski and Matt Kale and Metz and Shmuel Weinberger. But what you can do is you can specify hypotheses in terms of a sampling procedure. And for confidence intervals, things are a little bit easier. There's good theoretical foundations that say that if you sample a lot of points, enough points, then you can achieve good confidence that whatever the underlying structure was, you can pull it out. OK. But an easier thing to do, as described, is to project this into R or into Rn's. You take a number or a vector of numbers somehow out of your distribution of barcodes. And now it's much easier to specify hypotheses. You can get confidence intervals, and in some cases, sort of classical asymptotics gives you formulas for how to deal with these. And this is maybe the message to take from these slides is that the universe of traditional, there are things that are harder because it's harder to understand what's going on in the barcode space, but in general, the universe of traditional statistical procedures is available here to do inference about your data. And I'm sort of running to the end of the talk. And so one thing that I wanted to mention quickly that I haven't told you, and this is sort of a signpost for people who know about these things, is that there's been a lot of excellent work on the use of the Euler characteristic. Now, the Euler characteristic is a classical invariant. I mean, this, well, it goes back to Euler and maybe earlier. And the idea is that if you have a simplicial complex, you can take an alternating sum of adding up the vertices and the edges and the faces. And you can generalize this to the homological setting. And it turns out that this is much more robust and much easier to compute even than homology. Homology is easy to compute, but this is even easier. And here, theoretical foundations are much more tractable. And in particular, Adler and his student Taylor have done really excellent work on what you expect by looking at Euler characteristics of Gaussian random fields. So that's just, you have a plane, and you have some sort of random Gaussians on that producing your signal. And there's another very interesting piece of work to talk about, again in passing, which is that Turner and Mukherjee observed, so let me motivate this by saying that there's a problem of comparing teeth. So archaeologists have lots of teeth, which we regard as surfaces, two-dimensional surfaces in 3 space, and they'd like to think about the distance between different teeth as a way to understand speciation. it turns out that a very nice way to do this is to take slices through the teeth, take the Euler characteristic of the slice, and then consider the vector of all of those. And that's a sort of aggregate topological invariant of the tooth. And there's been, Turner and Mukherjee have done very nice work on using this to cluster the teeth as sort of an application of these topological methods. OK. So let me talk about sort of a little bit about now what some outstanding questions. So one sort of lesson is you can do statistics on these spaces of topological invariants, although certain things are harder. But a question that one might wonder for the future is that, and this is particularly relevant to this conference, is that no one has really run this on really very, very large data sets yet. We just don't know. And I think that there's lots of interest in doing this. There are lots of people trying to do it, but it's not clear yet how that will go and what that will look like. So you should do it. There is one exception to this, which is that there's a version of these tools called Mapper, which I'm going to tell you about this afternoon, which has been applied to large data sets. And in contrast to this talk, there will be fewer formulas and more pictures. And in particular, I'll tell you about the basketball example that Mike Lesnick mentioned, as well as a breast cancer application. Now, there are a bunch of other interesting questions. Sometimes your samples just come to you, but sometimes you can choose where to get new samples. This is particularly relevant if you have an enormous amount of demographic data, for instance, and you can pick sort of where to go in that based on what you see. And we don't know yet a lot about guided sampling. I think there's very interesting work to do there. Another one is, and this is a point that I made earlier, the intuition that people have about this is about, I'm sampling from a manifold. I'm sampling from a smooth object, like a coffee cup embedded in 3-space. So my samples came from this bottle. And that's, from a mathematical perspective, that's a wonderful model. In your life, that's not usually the kind of data you see. Natural images have that structure to some degree because they represent the world. But if you think about, if your metric space is genome expression data, so you have a vector of protein expression levels that you got from someone's tumor, and you look at a metric on those, and I'll tell you about a data analysis problem like that this afternoon, in that particular case, you don't expect that metric to have sort of fine, smooth geometric structure. And so there's a real question of to what degree is our intuition about the behavior of this correct, beyond what the theorems tell us. And, and I think that there's a lot of sort of evolving work about how to think about that. And the last thing is that, and this went by rapidly, but my advice to you in this talk about how to handle computing summaries. So, I take these barcodes from these samples. I'd like a summary barcode or some sort of topological summary. And my advice to you earlier was, well, turn it into a bunch of numbers and take the average, or take the median, which is in some ways unsatisfying. And I think that there's opportunities for lots of good work on trying to understand a more topological perspective on what you might do to summarize distributions of data and how to visualize it. And that, I think, is about it. So.
OK. My guess, just my guess, is that for most of you, this sounds very theoretical. Probably. This is typically when, some part of pure mathematics start going into applications. So I think this is typical. This is typical to what is going on. But let me tell you a couple of things. First, at 4 o'clock today, Andrew is going to give you, let's say, real applications of what they are saying first. And the second thing that for the most skeptical people here about this methodology is that, by now, the founders of this methodology, Professor Gunnar Carlsson and so on, they have already founded a company. This company is called Ajazdi, and you can find it in the internet, okay? And they are selling the methodology to the real people, okay? So for the skeptical people that maybe by now they think that this is sounds like, you know, algebraic topology. What is that? You know, it turns out that already this is being solved. Okay, like a methodology. So this is just a couple of things that I wanted to say about real application of what Andrew and Mike were saying.